Hey guys, it's Virginia, and I'm going to go through Practice Exam 3A. My email's there in case you want to contact me. And don't forget that as we're going through this exam, that it's useful to you guys if you all get your pencils and paper going and practice punching everything into your calculator. Okay. You don't want to be a backseat problem solver because I won't be there to talk you through it during the exam. Okay, let's get into it. This first question is talking about hydrogen peroxide, which we use in a bunch of demos because it's pretty reactive. One of the reasons for its reactivity are these different oxidation states. So the whole idea with oxidation numbers is we're going to assign each atom its own oxidation number, and we want all of the oxidation numbers to add up to be the overall charge on the molecule. Here for hydrogen peroxide, our molecule's neutral, so we'll need all of the oxidation numbers to add up to be 0. Down in the corner, I've written suggested oxidation numbers. And so this can give us an idea of where to start assigning oxidation numbers. So the alkali metals, our sodiums, potassiums of the world, tend to have an oxidation number of +1. The alkali earth metals, like calcium or magnesium, have a +2 oxidation number. Fluorine has a -1. Hydrogen likes to have a +1. Oxygen likes to have a -2. And halogens like to have a -1 oxidation number. And the reason I've written it this way is because these are written in terms of increasing strictness. So the alkali metals are in charge. They're the most strict. They're the most rigid with what they want their oxidation number to be. It's always going to be +1. And if they're combined with anything below, those are going to have to adjust to make sure that the alkali metals are always +1. So when I have a molecule that I'm going to assign for, I'm going to look at the atoms there. So I have hydrogen and oxygen. And I'm going to start with whichever one's higher on this list. So I'm going to start with hydrogen and give it its +1. I have 2 hydrogens overall, so this will be overall +2 contribution from the hydrogen. The molecule's neutral, so I need the oxygens to contribute an overall -2. There's only one oxygen. Or I'm sorry, there's 2 oxygens, so each oxygen is only going to be -1. Okay, and so there are the oxidation numbers. You'll notice that oxygen doesn't have its preferred number, and that's because we give the priority to hydrogen here. And this ends up being true for any peroxides, not just hydrogen peroxide. Okay, so then our oxidation state for the oxygen is just going to be -2, or -1, sorry, -1. Okay, next up we have a 0.1 molar solution of some weak acid. They want us to figure out what's true. Okay, so the first statement says the pH of the solution is going to be equal to 1. So, if we pretend that we have a strong acid, so if this were strong, we could say that the concentration of HA is equal to the concentration of H+, and they're both just then 0.1 molar. And then we could go ahead and say pH is equal to negative log of that, which would then be 1. But our acid isn't strong, right? They tell us it's a weak acid. Okay, so that can't be true. Our pH is going to end up being higher than that because we're not going to completely dissociate into protons. Okay, and part of being weak also means we're not dissociating and completely into protons, but also we're not dissociating very much. And so B seems to make sense, that we would have a lot more of our original species than its conjugate, which then rules out C and D, because we're assuming it's not breaking apart very much. We're also not going to have very much of our conjugate acid, so we don't have our Ka, so we can't solve for our conjugate base concentration, but we know that B is the answer, so we can rule out E. In number 3 here, we have 3 solutions, and we're going to add some water to them. Okay, so our first solution is KCl. This is a salt. It's a strong electrolyte. It's going to break it up into K plus and Cl minus. The second solution is HCl. This is a strong acid, so it's going to completely dissociate into H plus and Cl minus. And thirdly, we have KOH, which is a strong base and will completely dissociate into potassium and hydroxide ions. Okay, if we think about classifying the ions here for KCl, those are both spectators, and so we're going to start with our pH being equal to 7. And so if we add water, which is, neutral, to something that's neutral, it's just going to stay neutral. Okay, so that one's pretty easy to think about. For this next one, we have our strong acid. And so what we have to kind of think about is that when we add water, we're going to decrease our concentration of protons because we're diluting the solution. And so for decreasing our amount of protons in solution, we'll end up increasing the pH. Okay, and we can use the same thought process for looking at the KOH, because we have the hydroxide, which makes the solution basic. Then we add water, and that means we're going to decrease our concentration of hydroxide, and so the pH will go down. Another way you can think of this is we're adding in something that's coming in at a pH of 7, and so it's going to kind of pull the pH towards 7. Okay, so being able to classify your solutions and think about their starting pHs will help you think about this problem. And this makes the answer B. Okay, for number 4, they want us to figure out the molar solubility of cadmium hydroxide. And they tell us that the solution is buffered at pH 9. And they give us the KSP. So the first thing I want to say is that when they ask for the molar solubility, really they're asking for the X from the ice table. Okay, and they give us the KSP. We can go ahead and write an expression for the KSP. And so we're just going to write this like any KEQ expression, where we'll have aqueous and gaseous components included, and so we'll only have our products. We'll have CD 2 plus times OH minus squared. Okay, but they also tell us this part about the pH equaling 9. And so pH, we know we can relate to proton concentration, but we can also relate it to POH, and then relate it to our hydroxide concentration. So what we're going to do is figure out what the concentration of hydroxide is and use that throughout then. So our pOH is just going to equal 5, 14 minus 9. And so this is going to give us a concentration of hydroxide equal to 10 to the minus 5th molar. So now we can go ahead and set up our ice table. We're going to disregard the solid. We haven't started with any cadmium, so we're going to have 0 molar of that to begin. But we know how much hydroxide we have floating around. We figured that out from the pH, and this is just going to be 10 to the minus 5 molar. Okay, that concentration has already accounted, or it's coming from somewhere else, so we don't need to worry about the stoichiometry. Okay, that's coming from the buffer keeping the pH constant, which means we're keeping our hydroxide amount constant. So I'm also just going to say there's no change for the hydroxide. We're intentionally buffering the solution to keep pH and pOH constant. So our equilibrium concentration for this will also be 10 to the minus 5. But we don't know how much cadmium is going to come from this dissociation. So we'll add 1x and just have x for that final concentration. Okay. And so we can go ahead and take our KSP of 2 times 10 to the negative 14 and set this equal to x from the cadmium times 10 to the minus 5 squared for the hydroxide. So in our equilibrium, we do need to keep the stoichiometry in mind when we're writing our KSP expression. And even though the hydroxide concentration is coming from somewhere else and being controlled by another outside source, it's still going to affect our equilibrium in this way, so we need to keep track of it in our KSP expression. When we solve for x, we get that x is equal to 2 times 10 to the negative 4 molar. And so that's going to be our molar solubility. And what's cool about this is it didn't matter how much cadmium hydroxide solid we started with. We could have had a kilogram or a gram, just as long as we had enough to saturate the solution. We could have put 10 kilograms in, who knows. Okay, now we have this titration curve, and they want us to figure out what it could be between. So we have A and B, and so if you imagine what's going on, we have our Erlenmeyer flask that we're adding stuff to, and this is flask A, and then we have our burette, not a very good burette, but that's adding something into that solution A, and so this is solution B. Okay, so let's look at the curve now. Here we have a starting pH around 2. So that would be when we only have solution A around. And so solution A is starting with a low pH. That tells me solution A it's definitely some kind of acid. And then because as we add B, the pH increases, that tells me that B is some kind of base. Okay, next there are a few different features we could look at, one of which is about here. And this is where the curve is kind of flat. And so when it's flat, that means the pH isn't really changing even as we add base in, which makes this the buffer region. And that point in the middle, the pKa. And so because we have this buffer region and some pKa, that tells me that A is a weak acid. And then once we get through this pKa part, we have an inflection point here, which is the equivalence point. And it looks like for this curve, the equivalence point is at a pH of about 8. And so when you have a weak acid plus a strong base, you have a pH at the equivalence point that's greater than 7. And so that tells me that this is a strong base. Okay. If we instead had a strong acid, strong base titration curve, would take this really steep shape. So because it's kind of a more stretched out version, that tells me that we must have a weak species present. And so the answer here is E. Okay, for number 6, we're looking at adding some salts to pure water, and we want to figure out what will increase the pH. And so we know that increasing the pH means that the salts must be basic. Okay, so let's go ahead and think about each of these salts individually. We can start with KBr. So when we dissolve KBr, it's a salt, it'll completely dissociate into potassium and bromide ions. Okay, then we can think about kind of their origin. And so potassium ions you might recognize as coming from KOH. KOH is a strong base, so potassium's going to be a spectator. So I'm going to go ahead and just draw a line through it because it's not going to affect the pH. Br minus you might think of as coming from HBr. HBr is a strong acid, so its conjugate is going to be negligible and have no effect on the pH also. So KBr is going to be neutral, so it's going to have no effect on the pH. Okay, KCN is another salt. It's going to dissociate completely into K plus and Cn minus ions. So we already talked about how potassium is a spectator, so I'm going to cross that out. And then we can think about cyanide. So if we have something negatively charged that we're unsure about, we can just think about adding a proton back to it. So we'll have HCN, and this isn't a strong acid. This is a weak acid. So that means Cn minus is going to be its conjugate base. And so this will be a weak base. Okay, so KCN will increase the pH. And now we can look at iron bromide. This will completely dissociate to Fe3+ and 3 Br minuses. And so we already talked about how bromide is going to be a spectator, so we can ignore that. Iron, though, is a little different. This is a bit of a flashback to exam 2 material, but here we have a super positively charged and very charge dense cation. And so iron here is actually going to leave us acting as a Lewis acid. Okay, so that iron ion in water is going to combine with water, keep an OH to itself, and kick protons into solution. It'll hydrolyze the water and make it acidic. Okay, so it's definitely not going to make it basic. So that one's out. Okay, and then we can think about this NaClO4. As that dissociates into sodium ions and perchlorate ions. And so then we can think about where those may have come from. And so we can think of sodium as sodium hydroxide. This is a strong base, so the sodium is going to be a negligible acid. It's not going to affect pH. It's a spectator. And then we can think of the perchlorate as coming from HClO4. This is a strong acid, so the perchlorate is going to be a negligible base, no effect on pH. So that salt's also going to be a neutral salt. And then we just have one final salt, NH4Br. So we'll get NH4+ and Br minus. Bromide we already discussed as being a spectator. The NH4+ leaves us with a nitrogen with 4 bonds and no lone pairs. And so what that nitrogen is going to do is want to give up one of those protons so it can reform its lone pair and be negative or neutral. Okay, so this is going to be a weak acid. Nitrogens with 4 bonds are weak acids. And you can also think of it as being the conjugate of NH3, which we know is a weak base, making its conjugate a weak acid. So that would actually decrease the pH, so it's still not an answer for this problem. And the only answer is 2, the KCN. For number 7, we're trying to figure out the concentration of hydronium ion in pure water. And we're at a different temperature than normal, so they give us the pKw for that temperature. And so I'd like to point out that hydronium ion, this is H3O+. But we use that just as a synonym for H+. It's just whether it's connected to water that's in solution or not. And so if you know hydronium, you can use that interchangeably with proton concentration. So here I've written the autodissociation for water. So we just have pure water in solution. And we know that we can write the equilibrium expression for this. We get that Kw is going to be equal to just the concentration of protons times the concentration of hydroxide. We're not going to include the water because it's a liquid. Okay. And then if we want to, we can go ahead and take the negative log of this and say that pKw is equal to pH plus pOH. And they tell us that at this concentration the number is 12.7 for pKw. And so for pure water, we know that our concentration of protons and our concentration of hydroxide are equal, which is what makes pure water the definition of neutral. Okay, so this is going to be neutral, even though we're at a different temperature, and we'll get different pHs and stuff out of it. And so here we can just say pH is going to be equal to pOH, which is just going to be equal then to half of 12.7. So this is going to be equal to 6.35. Okay, so they're asking us for a concentration of hydronium, which is like concentration of protons. So we can just take that we know now, that pH is equal to 6.35, and say that our concentration of protons then is equal to 10 to the negative 6.35, which is equal to 4.47 times 10 to the negative 7 molar, which I would then just call B. So just because the pH of pure water at this temperature is 6.35 doesn't mean that it's acidic. It just means that our definition of neutral is a little different because we get less of this dissociation. Okay, in this problem, they want us to figure out the percent ionization of this phenol solution based on what pH we get after we add it to water. So percent ionization is a way of saying how much of our original weak thing splits apart into ions. And so what we can do is pick one of those ions, in this case we can use protons, and divide it by the original species concentration. And then we'll just multiply it by 100% to make it percentage. And so we know our original concentration, because they just tell it to us in the problem, it's 0.56 molar. So we need to figure out our concentration of protons, but we're kind of spoiled here because they gave us pH, which is a direct link to proton concentration. Because we can say then that our concentration of protons is equal to 10 minus 5.07, which is 8.51 times 10 to the negative 6 molar. So we can bring that number in up here for a numerator. Multiply that ratio by 100% to get our percent ionization, and it ends up being 1.52 times 10 to the negative 3%. So pretty small percentage, and one that happens to correspond to A. For number 10, we have this barium hydroxide solution that we're dissolving. And barium hydroxide's a strong base, so these arrows that I wrote here are wrong, right? We should have complete dissociation into barium ions and hydroxide ions. And so we have this 0.02 molar to begin with. And we get 1 barium out for every 1 barium hydroxide. So this is going to be 0.02 molar also. But we get 2 hydroxides out for every 1 barium hydroxide. So here we'll have a solution of 0.04 molar. So, the barium ions are spectators, right? They're not going to affect the pH. The hydroxide ions will though, and we know their concentration. So we can go ahead and figure out what the pOH is. This is going to be the negative log of 0.04, which gives us a pOH of 1.4. So then we can say pH is equal to pKw, which is 14 at 25 degrees Celsius, minus pOH. And so our pH here is just going to be 12.6. And this makes sense, right? Because we have something that's a strong base, so we expect that this is going to be above 7. So it checks out. Okay, don't forget that final step.